Welcome to Math 1300, Nunez Community College. This section is section 3.3. This section is known as piecewise functions and odd, even, and neither functions. The first thing that we want to do is we want to determine what makes a function odd, even, or neither. So we have even functions first. Even functions have symmetry. Symmetry is like if you take something and you cut it, like you cut someone's face, for instance, into two equal parts. There's a right side and a left where there's an eye on both sides, an ear on both sides. Symmetry means it would look the same on both sides if you open it up, sort of like a book. Even functions have symmetry with the y-axis. Has symmetry with the y-axis. So if you open it, a function that has symmetry with the y-axis would be the same on the left and the right of the y-axis. One even function would be an absolute value function. We have odd functions. Odd functions also has symmetry, but an odd function has symmetry with the origin. Has symmetry with the origin. An odd function might be like x cubed. So an odd function would come down and go pass through the origin. It's almost like you would take it, flip it up on the origin, and flip it around, and then put it back down. So an odd function would be f of x is equal to x to the third power. A function that is neither has no symmetry with the y-axis and no symmetry with the origin. Okay? We are going to first of all be asked to determine or to find whether each function is odd, even, or neither. On this, they're probably going to ask us to list the steps. So in order to list the steps, we have to know what steps that we need to put in. So we take a function, for instance, f of x is equal to x squared plus 1. Okay? And we want to determine whether or not it's odd, even, or neither. The first thing we do is we plug in a negative x. We plug in a negative x for x in the function itself. When we plug in a negative x, it's negative x squared plus 1. Once we plug in the negative x, we evaluate. Negative x squared means negative x times negative x. Negative times a negative is a positive. X times x is x squared. So negative x squared is just x squared plus 1. So we plugged in the negative x, we evaluated, and what we came up with once we evaluated is what we started with. If we originally come up with what we started with, then this is known as an even function. So we always do the same thing. We plug in a negative x where we have x's, we evaluate, and if we come up with the same thing that we started with, then it's an even function. I'm going to leave that one up there so that we can look at the next one, which is going to be, well, let's see, probably an odd function. Suppose I have f of x is equal to x to the third minus x. F of x is equal to x to the third minus x. Well, our steps is going to be plug in a negative x wherever you have x's. So this is going to be negative x to the third. Remember, the whole thing is to the third, so it's in parentheses. Minus negative x. When we now evaluate, we're going to come up with negative. There's 3 of them, so it's going to be negative. And it's x to the third. Then we have minus a negative, which is a plus x. So f of negative x, we look at it and we say, does it look like where we started? Well, no. Opposite signs, opposite signs. So since it's not the same, it is not an even function. Our next step then is to factor out a -1. F of negative x, factor out a -1. What does it do? It changes the signs. This becomes a positive x to the third. This becomes a minus x. After we factor out a -1, we then ask, does this look like where we started? And the answer is yes, it does. So if we factor out a -1 and it looks like where we started, it's an odd function. It's an odd function. So even if we put the -x in and it evaluates to be the same thing, even. If we plug the -x in, it does not look the same. We then factor out a -1, it then looks the same. It's an odd function. And finally, let's look at one more. Suppose I have f of x. Suppose I have f of x equals x squared minus x plus 1. X squared minus x plus 1. Steps always the same. Plug in a -x. Plug in a -x. Evaluate. This becomes x squared. This becomes plus x. That's plus 1. Ask ourselves, does this look like where we started? Here I have a plus x. Here I have a minus x, so it's not the same. So we're going to factor out a -1. That changes the sign. That changes the sign. And that changes the sign. Does this look like where we started? No. So if we plug in the -x, evaluate, it doesn't look like where we started, we factor out a -1. If it still doesn't look like where we started, then it's not even or odd. It is neither. It is neither. The next thing that we're going to have to try to look at is whether functions are increasing, decreasing, or constant. Whether functions are increasing, decreasing, and constant. And for that, we're going to look at a graph. For that, we're going to look at a graph. If the graph is increasing, then the graph is going uphill, or a positive slope. The graph is moving uphill, a positive slope. If it's decreasing, then it's moving downhill, or a negative slope. And if it's constant, then it is a horizontal line moving side to side. Now what we're going to look at is we're going to look at the intervals where the graph is either increasing, decreasing, or constant. Intervals meaning in the sets of numbers. So if we look at a graph of, like, let's say it's a quadratic. F of x is equal to x squared. The fact that it's quadratic doesn't mean that much, but that would be the picture of it. If it is quadratic, we're going to talk about this arrow being the leftmost point of this graph. And that's where we want to start. We want to start as far to the left as we can. We want to end as far to the right as we can. So if I come way over here to the left and I'm walking to the right, what's happening? Well, I'm coming downhill, coming downhill, coming downhill. So from this point, which is -infinity, because that's the smallest point that we can have as far as to the left, as I'm moving to the right, which is all the way to this point, which is at 0, from -infinity coming all the way to 0, the graph is decreasing. So it's going downhill as I'm moving towards the right. And it never, ever touches infinity. And at 0, it's no longer decreasing. It's actually making a turn to go the opposite way. So that would also be a parenthesis. So from -infinity all the way to 0, the graph is decreasing. At 0, it starts changing. At 0, now I'm still moving to the right, but now the graph is going up. And if the graph is going up, it's increasing. So it's increasing from 0 all the way to, not looking up, but looking to the right, all the way to infinity. It's increasing from 0 all the way to infinity. So that would be the graph decreasing from negative infinity to the point where it starts to make the turn. So from negative infinity to 0, and then from 0 on, it's increasing, moving up. Let's look at one that may have a little more, maybe of a challenge, a little more things that it's doing both. So suppose I have a graph that starts here at -7, -4, and then goes to -2, 2, and of course these are my points, and 1, -1, and then up to 4, 3, and then to 7, 3, and it's doing this. It's supposed to be horizontal. And then, so the first thing I want you to notice is this left end has a point, the right end has an arrow. So it means it's going to keep on going to the right. But on the left, it's starting at this point. It's starting at this point. So from -7, which is where we're starting, if we start going to the right, what is happening? The graph is increasing. And it's increasing until we get to this point here, which is -2. From -7 to -2, the graph is increasing. Again, that's the interval. Starting at -7, going all the way to -2, it's increasing. At -2 is where it starts doing something else. It makes the turn. So we stopped off at -2, we're going to start at -2. So at -2, we keep on going. What's happening now? It's falling. So it's decreasing. And it's decreasing from -2 all the way until we get to the number 1. So from -2 to 1, it's decreasing. Then we left off at 1, so we're starting back at 1. What happens at 1 as we keep going to the right, it's now increasing again. And that's from -1 all the way to +4. -1 to +4, it's increasing. Then at +4, where we left off, that's where we start. At +4, it all the way until the number 7, it's what? It's supposed to be horizontal, so that's constant. And then from 7 on, it's what? Falling. So it's decreasing from 7 all the way to infinity. 7 all the way to infinity. Now you must remember, this is called the domain at which it is increasing, decreasing, or constant. The domain is always the x values. So what I'm worried about here is the x values from here to here where it's increasing. I'm worried about the x values from here to here where it's decreasing, and so on and so on. The y's are really not telling me anything that I need information-wise, except for the fact that it's decreasing or increasing. It's the x values, which is the domain, that I'm looking at when it comes to increasing, decreasing, and constant. Okay, in the next example, we're going to look at something called maximas and minimas. Maximas and minimas are points on a graph that are the highest points or the lowest points over a certain domain. So if I have a graph that's doing this, for instance, then this point right here is a low point. But it's a low point over a certain domain, a specific domain from side to side. So this is called a minima. Make sure what spelling on that. M-I-N-I-M-U-S. Okay, minimum. And here is another low point, so that's also a minimum. Both of these are low points. That's the minimum points that we have over specific domains. From here to here, that's the lowest point, that's a minimum. From here to here, that's the lowest point, that's a minimum. And these will be called local minimas, because it's only local within a specific domain. It's only local within a specific domain. The high point that we have is called a maxima. Okay? And again, it's only the highest point over a local domain, so it's called a local maxima. So high points are maximas, low points are minimas. They're local if it's only between a specific domain. It's only between a specific domain. So on this one, we want to look at a graph that has some points given to us. And remember, the local maxes and the local mins are at the x values. They're at the x values. So it's at the y values. So we're looking at the y value to see what the local max or the local min is. Where it occurs is at the x value. So if I have something that looks like this, and let's say that this one is 3, 2, and let's say that the other one is at 5, 6, and I'm trying to find a local minimum. And a local maxima. Okay, the local minima would be here, and that would be 2. The local maxima would be here, and that would be 6. All right, now the next part, we're going to look at something called piecewise functions. Piecewise functions. Piecewise functions. Piecewise because it's the piece of a function and then a piece of another function. It could have infinite number of functions, but usually we have 2 or 3 functions. We're looking at, for the piecewise function, over a certain domain. So over a certain domain, we're looking at one function. As we increase or decrease the domain, we'll be looking at another function. It could be written like this. It says, find each of the following values. We're looking at f of x, which is the function, and they have it in braces because there's more than one. They may have something like -2 if, in this case, x is less than or equal to 0. And they might have x plus 1 if x is greater than 0. And they're going to ask us to evaluate. They're going to give us numbers for x, and we're going to have to choose which function do we use, whether x is less than or equal to 0 or whether x is greater than 0. They may ask us to find f of -3. They may ask us to find f of 0. They may ask us to find f of 1 and f of 2. So that's 4 things that they're asking us to find. If they ask us to find f of -3, I'm looking to see what domain I'm in. -3 means that x is less than 0, so I'm going to use the top. The function says that it's equal to -2. We don't have to do anything with it. We find the right function. If there is an x, we would plug it in. There's no x, so the answer is just -2. If I look at f of 0, this says x is less than or equal to 0. So again, I'd use the top function. The answer would be -2. Any number within that domain, the answer is always -2. If I looked at the other one, f of 1, 1 is when x is greater than 0, so I would plug it in. This would be 1 plus 1, which would be the number 2. And for the last one, f of 2, again, the bottom function is the one we use because that's where x is greater than 0. I would plug it in, 2 plus 1, the answer would be 3. And that is piecewise functions. And that also concludes section 3.3. I will see you at the next one.